No signal. Ugh. Does anyone know what Chris did, the magic he did? Okay, I'll turn it off. Turn it back on. I don't know if I think it has to cool off the fan clip. Well, let me try it and see. Oh, it's trying. What is going on here? Well, when you hear the fan go off, let me know. I'll try it again. Okay, where we were last time. Yes. Second? I can't hear.
On page 457.
Something 57?
457.
457? Okay. Get this in my place. Okay, 457. Number 7. 3 charges are located along the x-axis. Okay. What I'm going to do here is minimize that and that. Whoa. Look at here. All right, what chapter was that you had the question about? Basic electricity, 17? Not yours, but the other one. I think that was basic electricity, right? Okay. And what was the question?
It went off.
Yes.
My question?
No, the question was earlier.
On number 10. Number 7.
Okay, what voltage is required to produce a current of 2.85 amps in the circuit indicated? See, what I see on here, it chops off the end, so I thought it had all the information in it. So let me go back and change what I just told you, so we'll be in agreement. Okay. Okay, can I bum the calculator again? Hold on, up on my computer here. Okay, make that a 7 ohm resistor. I think I said 4 before, make it a 7. Okay. All right. Go back to this. This is taking forever to do tonight. Sorry about this. Okay. We'll start the slideshow. We are recording, but haven't got much to record. We'll go from current slide. There we go. Now let's see if this will turn on. Ah, look at that. Same thing we did before, this time it worked. I wonder if there's some sort of a short somewhere between here and there, and sometimes it connects and sometimes it doesn't. Okay, let's get back to yours then, Mary. This is page 457, 7.3. Okay, well, let me get my pen activated. Okay, page 427, it's problem 17.3, number 7, didn't you say? Okay, 3 charges are located along the x-axis. Charge A at plus 3 microcoulombs is located at the origin. Okay, so here's the x-axis, and here we have 3.00 microcoulombs. This is charge A, okay, and that's a positive, okay, located at the origin. Charge B, 5.50 microcoulombs, is located at x equal 0.4 meters, okay. So 1, 2, 3, 4. So this is at 0.4 meters, and this will be charge B, and that's 5.5, positive 5.50 microcoulombs. Okay? And charge C is located at 7.5. So there's 5, 6, 7, 8. So there is charge C, and this is a minus 4.6 microcoulombs. Okay. The A part of this problem says find the total force and direction on charge B. Okay. And your formula is just on the previous page there, that the total F is K Q1 Q2 over R squared. Okay? Now, The K is Coulomb's constant, which is 9.00 times 10 to the 9th Newton meter squared per Coulomb squared. Okay? Now, there are two forces on B. Find the total force and direction on charge B. Okay? The first is the force from charge A. Now, from charge A, this is a positive, that's a positive, so the force is in that direction. So this is what I'm going to call FBA, force on B by A. Okay? And that's what we'll do here. B by A. Okay? And that's the K times the charges, 3.00 times 10 to the microcoulomb is 10 to the minus 6 coulombs. And charge 2 is positive 5.50 times 10 to the 6th minus 6 coulombs. And this is divided by the distance 0.4 meters. 0.4 meters squared. Okay? Got it? Now, I'll do the denominator at 0.16 square meters, and that's going to cancel out the square meters that are up here, and your Coulomb square here will cancel out these two coulombs. So basically what you do for this first part is 9 EE or EXP 9 times 3 EE or EXP negative 6. Make sure the negative there you have is 1 in parentheses. 5 times 5.5 EE or EXP minus 6 again, and divide that by 0.16. Okay? And that will give you so many newtons. Okay? Have any of you done that yet? Or meanwhile, I'll set up the next one. The force on B by C is same thing, 9.00 times 10 to the 9th Newton meter squared per Coulomb squared times, and this time it'll be 5.5 times 10 to the minus 6 microcoulombs times 4, is it 4.6? Yeah. 4.6. And you don't have to put the signs in there. I'm afraid they'd probably confuse you, so just leave those off. 10 to the minus 6 microcoulombs, and divide that by the difference squared. Now, I didn't write that down. That's 0.75, wasn't it? Yeah, 0.75 meters. 0.750 meters. Okay? All those are positive. So that's a 0.35 would be the distance of that, 0.350 meters squared. Now that one will also be in that direction, F sub BC, because you see it's a negative charge, C is a negative charge, and B is a positive charge, so it's pulling it that way. That was in the problem, wasn't it? Number 7. This charge C is located at x equals 0.75 meters. What's that? I can't hear.
I thought of there you looked at 0.850
I'm sorry?
on the blackboard.
This down here?
Yeah.
Okay, because it's 0.750 minus 0.4. The distance between these two is 0.35 meters. 0.350 meters. Right? That's the distance between the two. Okay? Now, I don't have a calculator. Well, let's see. Maybe I can do it on here. Let me. It's going to be hard without. Can I bumps? Yeah. Okay.
You can hold on to it.
No. Okay.
If you want to.
Okay. Let me see if I can figure out how to operate it. 9. This calculator is EE9. That's that. Times 3 EE negative 6. Okay, on your calculator, you press the 6 and then do the plus minus key. Okay, times 5.5 EE negative 6, and divide that by 0.16, and that gives you a force of, oh man, this one right here is 0.928125. 0.928125. To the left. Right, I'm sorry, to the right. Okay? Now, the bottom one is 9 EE9 times 5.5 EE6 to the minus 1 times 4.6 EE6, change sign, and divide that by 0.35 squared. There it is. And press equal. And that's 1.858 blah, 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 blah. Okay? So I'm going to add that 1.85887 blah, blah, blah to 0.928125. And I get something close to, let's see, how many digits? 3. 2.79. So I get, we add those two together, 2.79 newtons. Because you see, the meter squares go out, and the coulombs squared go out. Oh, I put microcoulombs here. 10 to the minus 6 takes away the micro. Okay, sorry about that. Okay, so that's the A part. Okay. Does this one have an answer in the back? Before we go any further, make sure this is chapter 17. (17.3). 7A was negative 0.93. How, and no. Did I misread the problem here? Find the total force and direction on charge B. I do not agree with that, unless I've copied something down wrong. They say negative. It can't possibly be negative. So We're in newtons. There's nothing wrong with that. The coulombs or microcoulombs are 10 to the minus 6 coulombs. What they put down is the answer for just that first one, 0.93. That was from the force on charge B from charge A. And they didn't even take into account charge C. But that's how you do the problem. Then the second part says, find the total force and direction on charge A. Well, let's just see what it would be. Charge A is being repelled, so that would be a negative by charge B, but it's being attracted, but varies lightly by charge C. And so that would be a negative direction, and they have it as positive direction. So something they're doing is totally wrong there. And it said find the total force and direction, find the total force and direction on charge A, then C, find the total force and direction on charge C. And on charge C, it would be to the left, and they do have that one right. Okay. And 2.0 8.
You do it the same way you did.
Yeah, you just do the two charges, and I don't know why they have the wrong answers in the back. I don't know about the other two, but the first one certainly is wrong. It's going in the wrong direction and everything. Unless I read something wrong in the problem, which I don't think I did. Yeah. So it can't possibly be negative, and it would be quite positive in the other direction. So that's how you do the first part, and the other two parts are similar. Does that answer what you needed? Okay. But that's how you use Coulomb's law. Okay, any other questions before we get started tonight? Sorry, this is taking a while. So let's erase. Can I erase all the ink? Okay. All right. Tonight we are example 2 on page 510. And let's just make sure that, no, okay. Example 2 on 510, find the magnetic field at the center of a solenoid that is, so here are a solenoid, we'll use this picture here. This solenoid will be 0.425 meters long. That will be the distance from there to there, okay? And 0.0750 meters in diameter. So this diameter here will be 0.0750 meters there. That's a pretty big solenoid, okay? And has 3 layers of 850 turns each, okay? And it's asking for the magnetic field, so your B, the formula above that you see there, is mu naught I times N, okay? And it says, so 3 layers of 850 turns each, so your N here is the number of turns per unit length of solenoid, okay, turns per unit length. So I was going to say the N, let's call capital N the total number. That's 850 times 3, which would be 2550 turns, okay? But the little n is number of turns per unit length, so you divide that by the length of the solenoid. Whoa! So little n is 2550 divided by 0.425, okay? And that would be, what do you get when you get that? 6,000, that's what they got in the book. 6,000 turns per meter. Now the third decimal is the third significant digit. The third digit is your last significant digit, and this will be turns per meter. Okay? This was in meters. Okay. Now, the permeability constant mu naught was 4 pi times 10 to the negative 7, and that would be Tesla meters per amp. And your I here was your, I didn't read that far, 0.250 amps. Okay? Flows throughout. Okay? So you see what's important there. This formula is good when the solenoid is long compared to the radius. And that's the only reason they got the diameter in there. It is very long compared to the radius. So you can use this formula. So again, 4 pi EE or EXP, and depending on your calculator, 7 plus minus key or minus 7, whichever calculator you have, times 0.250 times 6,000. And the amps cancels out this amp cancels out that amp, this meter cancels out that meter, or this meter over here, and you wound up with Tesla. How many did you get? Write it down for you. 4 pi times 10 to the negative 7 Tesla meter per amp times 0.250 amps times 6,000 turns per meter. Okay, so the meters go out, the amps go out, and you're left with Tesla. It's going to be a pretty small number. I mean, relatively small. This is 6 times 10 to the third. That takes 3 of those away, so that gives you 4 pi times 10 to the minus 4th. And then multiply times a 0.2. By the time you do it all, what? Anyone get it? It's in. Whoa, no. Oh yeah, say it again, 0.00188. Is that what you were going to say? Yeah, okay. Or they put it 1.88 times 10 to the minus 3rd Tesla. Perfect. Okay. Then there's problems there. Problems 18.2. You can do any of the odds 1 through 13. Okay, now I have to remind myself how far we're going here. That was 18.1 and 18.2. I think we jumped down to 18.7, if I'm not mistaken. That's what I have in my front. And this is a very short section. So let's scroll on ahead. This is where we are. A charged particle that is not moving will produce no interactions with the magnetic field. It's only moving charges that induce magnetic fields. Only. Okay? You can have as big a charge as you want to, but if it's not moving, not producing any magnetic field. However, if it does move through a magnetic field, it is deflected by the field. The deflection force is greatest when the direction is perpendicular to the magnetic field lines. So in other words, the velocity needs to be perpendicular to the field. When that's the case, you're going to get maximum deflection. And that's what they're showing here. Remember, the magnetic field lines always go from north to south. Okay? And these are going to be very uniform field lines here because of it's a horseshoe magnet. Your velocity vector is coming in like this, okay? And then the deflection is that way. Now, why is it that way? It's V, velocity, cross B, which would be that way. This is hard to see by this drawing. Between the sources, let's see. Okay, the force that acts on a moving charged particle does not act in the direction between the sources of interaction, but is perpendicular to both the magnetic field and the direction of the charged particle. And therefore, their drawing here doesn't make sense because the field lines are this way and they have the deflection that way. The deflection would be up. Well, hard to say because it's an electron beam, so that might be heading downward. But yeah, they show the force being up. They show it being deflected this way, but it really should be being deflected this way. Okay? Perpendicular to both the incoming velocity and the direction. They've got this correct, and they have the magnetic field backwards. I mean, I don't know what they're doing, but anyway, this is right. If the field is this way, electron beam, the velocity is this way, and the magnetic field that way, then right-hand rule would have you that way, except there's an electron, so it's a negative charge, so you go the opposite way, and that would have the force being upward. And that's all we had to do in section 18.7. A moving charge induces a magnetic field. And when you got a moving charge in the presence of a magnetic field, you have deflection. Okay. So, let's go to chapter 18. By the way, there aren't any questions on 18.7, but there is a glossary there. Formulas, I can't believe that's the only formula they list. 2 formulas. And then review questions and review problems. Now, let's go back and see which sections we cover in 19. Two, 3, and I think it's 5. I had 4 marked, but then I think I tried to erase it. Does anyone have the syllabus open? I think it's only 2, 3, and 5. Okay? Now, why am I still in that? Oh, okay. Let's go to chapter 19. Well, this is being just as stubborn as it was earlier. There we go. All right. All right. And it shut down here. Oh, here we go. Yep. Alternating current electricity. Now, first off, y'all know what alternating current is. Direct current is when you have a positive pole of a battery here, a negative pole here. If they were moving positive charges, they'd be going from positive to negative. The electron circuit goes the other way, but it's only one-dimensional flow. Alternating current basically is just oscillating, and this illustrates it. At some moment, the current is, and let me get my pen darkened. The current is moving in one direction, then it stops, then it's in the other direction, then it stops and goes back in the first direction. So it's going positive, 0, negative, 0, positive, 0, alternating. Now, the charges are just doing this. They're not flowing down the wire. It's the field that's doing that, that's creating the charge like that. Now, this is just a little bit of introduction. If you had direct current, which is what we were doing in chapter 18, your power, which is the measured in watts, is all constant. The voltage is constant, and the current is constant. Okay? Now, if you have alternating current, because the power is instantaneous current times instantaneous voltage, and those are in phase with each other, okay? The current flows positive when the voltage is positive, okay? E is the voltage and I is the current. So the product of them is the power, okay? And then when they go to the 0, it's 0, but then when they both go negative at the same time, because power is the product of those two, it's always positive, okay? So the power doesn't alternate. It's not constant, but it doesn't alternate. And then the average power would be that line that sort of bisects those curves, okay? Don't worry too much about that. This is just a background information, okay? Now, well, actually, it's more than background information. That is the section we were on, okay? So let's back up here, and let me give you a couple formulas before that. This is 19.2 AC power, okay? Now, we said before that power is equal to voltage times current, right? If you remember Ohm's law, E is equal to IR. Remember that? And sometimes we use V. This book uses E. So if you substitute IR for E, you would get IR times I, which would be I squared R. And that's the first one that they list on page 528. Okay? They're going back and forth between the E and the V, but, you know, they're calling this V is equal to IR, which is fine. Okay. Now, the second one was that power is equal to V times I. Okay, remember what the book is distinguishing. The voltage across a battery is what they're calling E. The voltage drop across a circuit element is what they're calling V. It's a little bizarre they're doing it that way. But then on the other hand, you could say current is equal to voltage over resistance, That's also Ohm's law, right? And then you could plug that in for the current here. So your power here would then be V times V over R, which would be V squared over R. Your voltage squared divided by your resistance. Okay. Okay. So those are three different expressions for power. And if you think about them, all three of them indicate power is always positive, right? Because if voltage and current are in phase with each other, they're either both positive or both negative, so therefore power is positive. If you have I squared times R, I squared is always positive because it's a squared number, and your resistance is constant, so that's a positive number, so that would be positive. V squared, whether it's alternating or not, V squared is always positive, and R, of course, is always positive. So, by the way, yeah, they don't show it here, but R is always a constant. So, example 1 is this. What power is used in a resistance of 37 ohms? Okay, so I'm going to draw the I'm not going to draw, I'll just, yeah. So what power, we're looking for power, is equal, this is the unknown. Your resistance here is 37.0 ohms, and your current I is equal to 0.480 amps. Okay? So which one of the three formulas would you use here? Here's one, and here's one. Second? No. Here you weren't given V at all. You're given R and I, so use this one. I squared times R. So your power here would be 0.480 amps, and we don't really need the unit squared, times R, which is 37.0 ohms. You don't need that either, but that would give you your power in watts. So someone punch that in and see what you get. That'd be something around 0.2 times 37, so that would be 7.4. Is that right? No, 8.552. I was estimating. Okay, they got in the book 8.52 watts. Because power is always in watts. Okay? Now, I don't know if, oh, this is example 2, top of page 529. What power is used in a load of 12 ohms? So this would be the resistance, 12 ohms. I can't write. Okay, that's 12.0 ohms. If resistance, if the voltage drop across it is 110 volts, so your voltage drop is 110 volts. Okay? Which of the three formulas would you use then? V squared over R. So your power across that would be 110 volts squared divided by 12. Okay? And punch that in and see what you get. That's 12 ohms, by the way. 12.0 ohms if you wanted to be precise about it. Anyone got it yet? Okay, 1,080 you said? Oh, 0.8. Okay, 1,008 watts. Okay, now, what they're going to do, because you only had 3 digits here, 3 digits there, they're going to round this to 1,010. And then they're going to change that to kilowatts, because go with a smaller number, bigger unit, that'd be 1.01 kilowatts. Okay. Now, let's just look back. Here, the first example, 8.52 watts. That's very, very low power. Why is that such low power? Well, you had very low current. Very, very little current. 0.48 amps. And a pretty high resistor. So you're not going to get a lot of power out of that one. However, this one down here had a very large voltage, okay, and divided by a relatively small resistance, okay? So you're going to get a lot more current out of that, and that's where your power goes, okay? Now, then comes this, okay? The figure we've already described here. And the next thing they're going to talk about is transformers and power. They really sort of jump all over the place here, but let's go on and hit it. This is what we call a transformer, the basic components of a transformer. It says the uses of direct current in industry are somewhat limited. Primary applications are in charging storage batteries, electroplating, generating alternating current, and electrolysis, electromagnets, and automobile ignition systems. However, the AC can be changed to DC by a simple device called a rectifier, and that's basically all they say about it, okay? And they bring up those two formulas again. And then go to example 3. Now this is before we've gotten to this figure here, so maybe I should go back to my previous one and just clear the page, and we'll still keep using what we had before. A plant generates 50 kilowatts, okay? So the power here, they're giving you this, is 50.0 kilowatts. And it's because we usually use the base units, this would be 50,000 watts. But when you write it that way, you need to put the bar over it so you'll know which of those zeros is significant. Okay? Of power to be sent to a substation on line with a resistance of 3 ohms. Now that's not very much resistance. This is just your line loss probably. 3.00 ohms. Okay? We know that some power will be lost as heat during the transmission. The power lost is, so the PL, power lost is, and again, well, they are kind of jumping around here a little bit. They say the power loss is I squared R, because that comes more from the current than from the other things, but they didn't tell you anything about the current. So the power loss is I squared R. Now what you typically are trying to do is minimize the current, because then you minimize the power loss, okay? Because the current is what creates heat, okay? And you do that one of two ways, either by decreasing resistance, that generates a lot of current, or increasing voltage, that generates a lot of current. So one way or another, decreasing the resistance or increasing the voltage. Okay, so here's the A question with that given problem. How much power is lost? So again, we're looking for PL if the transmission is at 1150 volts. And what would be your parameter for 1150 volts? That would be your, and they either call it E or I. In this case, they're calling it V, sorry. E or V. I'm sorry, I said E or I. E or V. Okay? Now, so if V is equal to 1150 volts. All right. Well, they gave you resistance and now voltage. So your power loss here, we would use the other formula. Power is equal to, what was that one, remember? If you know voltage and resistance. V squared over R. Perfect. Okay? So this would be V squared over R. V squared was 1150 volts. I'm going to leave off the unit squared, divided by R, which is 3 ohms. Okay, that's a lot of power loss, folks. What do you get? 1150 squared is a huge number dividing by a fairly small number. It's going to be a lot of power loss. Anyone got it? Say again. 440. Say again. 833. Say it again. Oh, point. 3 something. Well, we don't need that many digits because we only got 3 significant. That would be 4.41. And that would be times 10 to the 345 watts. Or I would be tempted to say 441 kilowatts. That's a lot of power loss. Okay? Now they got wait a minute. Wait, back up, sorry. They're not using the power of transmission power. They're using the generating power, which is going to make it even worse, okay? So sorry about that. I can't for the life of me figure out why they're doing that, but we will do it too. Okay. This is the E is equal to 50,000 watt. No, wait. Sorry, I was misreading. Let me start over. Okay. And it's not at all clear to me why they're choosing to do this. They're saying how much power is lost if the transmission is at, and there again, if V was equal to 1150 volts. Okay? Now, they're going back. Okay, I'm sorry. Their power was 50,000 watts. The voltage is this, so they're coming up with the current. I is equal to power over volts. And that would be so they're using this power, not the one that we're looking for, but this power. That would be 50,000 watts divided by 1150 volts, and that gives you how much current? A lot, a whole lot of current. Well, not a huge number, but still it's a lot of current. What you get? 43.5. And that would be amps. Okay, then you take that and plug it in here. The power loss is equal to I squared, which is 43.5 squared times your resistance, 3.00 ohms. Okay, I shouldn't use the units. 43.5 squared times 3. It's going to be a lot. Would be close to more than 1,600 times 3, more than 5,000. Yeah. What you get? 5680 watts. So they rounded. And that would be about 5.68 kilowatts. Okay, so that's how much power they lose on the line. Okay, now what percentage of the power generated is lost in the transmission at 1150 volts? Well, percent would be the 5.68 kilowatts divided by 50,000, which is 50.0 kilowatts, and then you'll change that to a percent. That's better than 10%. What do they get? %11.4%. You probably got 0.114 and then multiply it by 100 and you get percent. Okay? Now C, how much power is lost if the transmission is at 11,500 volts? So we go back to the original problem here, and this is the C part, and you calculate the I if your power, again, is 50,000 watts, okay, divided by 11,500 volts. Isn't that what they said? Yeah. Your current has dropped to what? I'm doing this in my head, so I may be wrong, but I think it drops at the 4.35. Is that right? Yeah. Now, they've got an error in the book. In the book, they say 4.35 volts. That's amps. Okay. That is an amp there, not a volt. See, they got it right up above, but they got it wrong there. Okay. Now, so that's how much current. So we need to know power loss. So the power would be I squared over R. So it'd be 4.35 amps squared over 3.00 ohms. And what do you get there? No, I'm sorry, times. I wrote it wrong. Where's my pen? There it is. .35 squared times 3. It's going to be something, say again? 56.8 watts. Okay, so from 5.68 kilowatts to 56.8 watts, that's a huge difference. So your power loss is much, much less if you reduce the current. Okay, now how do you reduce the current? That's what we're getting to. Let's see what D is asking for. What percentage of the power generated is lost in transmission at 11,500 volts? Then that would be, this is the D part, this would be 56.8 divided by 50,000, because we're measuring now both of these in watts, so you got to have the same unit. And this is a very small number, about 0.114%. Is that what you get? Right. So you went from 11% loss to just over 0.1% loss. I'll go with 0.1% over 11% anytime. Okay? Now, so you see what's important here. If for long transmission lines, which is where you have more resistance, you need to drop your voltage, drop your current, which of course is going to have to increase the voltage. And how you do this is with transformers. And this is what a transformer is. It consists of 2 coils of wire wrapped on an iron core. Okay? Your primary core provides the AC voltage. Okay, AC, the alternating current source is there. It has to be AC. These transformers don't work with DC, okay? You have to have a changing current in order for a transformer to work. So it's coming in, you have a primary coil with, I'm going to point some things out to you. All stiff. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 turns, let's say. Maybe it's 10 turns on this side, and you have 1, 2, 3, 4, maybe 5 turns on that side. So this is called a step-down transformer. You feed in a large amount of voltage, and it drops the voltage over here. If that's 10 to 5, that is dropped by half. Your voltage is dropped by half, which means your current goes up. It doubles the current. But that's okay, because you came in with very low current but very high voltage. You don't want high voltage in your house. You want a fairly moderate voltage in your house, and you need a bit more current there. So this is a step-down transformer, dropping the voltage by the ratio of the number of coils. Okay? And I don't think they're going to show this, but let's see. Okay. Let's think about what's happening here. You have alternating current here. So you have a changing current. The changing current is going to induce a magnetic field. And that magnetic field is going to be changing very rapidly because the current is changing rapidly. It's going positive, negative, positive, negative. So that magnetic field is changing, and then this coil, it induces a current in this coil according to the amount of field change you had there. And because you had high voltage here, low current, then the power is the same on both ends, so you have to have low voltage and high current on this end. The voltage induced in the secondary coil by the magnetic field in the core. Because that magnetic field is constantly changing because it's alternating current. Now, let's see if they show this. I don't think they will. Well, seems like... Oh, okay. No, we'll get there in a second. Here is the formula that you use. VP, that's the voltage going into the primary coil. In fact, I think I like this better. VP is to NP. Oh, I'm sorry, they're doing it the other way. VS as NP is to NS. Now, what is that? The voltage in the primary coil, the ratio of it to the voltage in the secondary coil is the same as the number of turns in the primary coil. That's your NP is to NS in the secondary coil. Okay? So that's your basic formula for your transformers. Now this is assuming no power loss. And basically, your magnetic fields and things like this, they generally do have very, very low loss, okay, because it's just a field being changed. There's really not too much physical thing being changed, okay? So let's look at example 4 that we have here. A transformer on a neon sign has 100 turns in the primary coil. What would represent that in that equation up there? 100 turns in the primary coil. Which of those parameters? N to P is 100 turns. Okay? Okay? And 15,000 turns in the secondary coil. That would be N sub S. 15,000 turns. I would say this is a pretty powerful transformer. Okay? When the voltage applied in the primary coil is 110 volts, so what would that be? V sub P is 110 volts, which is normal household. We often say 120, but usually you have a little bit of line loss, so you would have 110. That's pretty common. And you're looking for VS, that's the unknown here. Okay? Just make a guess. Big number, small number? Big, really big. This is a step-up transformer. Okay? So you set up your proportion like this. 110 volts is to VS as 100 turns is to 15,000. Okay? And basically, that's a ratio of 1 to 150. So you take 1 here, multiply by 150, or you can do your cross multiplication like this. There's lots of ways you can do that, but basically you're going to have 150 times 110. So see what that gives you. V sub S is equal to 110 times 15,000 divided by 100. So these two zeros wipes those two out, and they have 110 is equal to 15 times 1500. What does that give you? Big voltage. What you get? 16,500 volts, and we could call that 16.5 kilovolts. A lot bigger. 110 to 16,500. Much bigger. Okay, and that leads to what we were talking about here, the two types of transformers, and I already mentioned this, not knowing they were going to show this illustration. This would be one similar to what we just did. Small number of turns on the primary side, large number of secondary, sort of step-up transformer. Now, what they're talking about here is the voltage is stepped up. If the voltage is stepped up and the power is equal, then the current is stepped down. But we don't usually talk about it. It's always the voltage we refer to. Step-up transformer. This would then be a step-down transformer because the number of turns on the primary side is greater than the number of turns on the secondary side. So the primary voltage would be large, secondary voltage smaller, step-down transformer. Now, do any of you have lights that come on outside, like illuminating a window or at night, or trees or things like that? You see houses that have that. Okay, those are usually low voltage, sometimes 6 volt, 8 volts. So they have, where they plug into the wall, you'll see a big old box there. That's a step-down transformer, taking the 110 or 120 down to 6 or 8. So it's really reducing the voltage. Of course, your current has to go up then, but that's okay. Okay, so there's a step-up and step-down transformer. Make sense? All right. Now, where are these important, or are they important? Okay. Well, let's see. They have some other stuff in here that I don't know if it's all that consequential to you. I wouldn't think so. I'll go back here. Some of you have your books, some of you don't. You should be fairly familiar with this one. That's the transformer you'll see outside your house or apartment or wherever you live. Find the power pole, power source, go back to the power pole on the street or alley or somewhere like that. You're going to see that. That's a step-down transformer. Always high voltage coming in, low voltage coming out. Now, around UAB, and I'm sure other areas too, you'll see areas that are fenced off. At UAB, I know there's a whole city block that's fenced off with chain link fence, probably razor wire on top, and maybe those slats like Venetian blinds that you can't see through very much. But if you peek through, you'll see big old transformers there. And those are, again, probably step down, bringing in a lot of high voltage and then bringing it down so that it can distribute around the college. There's probably some around here. I just don't know where they are here. Because, and I've never seen anyone do this, but they do it here, because the current is inversely proportional to the voltage, okay, because at constant power they've got, they're inversely related. They state the current equation, you might say, is IS over IP is equal to NP over NS, okay? I've never seen that expressed this way before. It's absolutely true, but I think it's far easier just to keep one formula in mind. the direct proportionality of the voltage, and keep that one in mind, and then go back with your power and figure out what the current is. That, to me, is the better way to do it than this. But they're going to do example 5 here, so let's do that. The primary current in a transformer is 10 amps. Okay? So IP is 10.0 amps. Okay, that's a pretty high current in most circumstances. If the primary coil has 550 turns, that would be N sub P is 550. That's turns. Okay. Secondary coil, N sub S, is 2,500 turns. Okay. What current flows out of the second coil? I sub S. Okay? Now, like I said, to me this can be a little confusing. If I were going to use something like this, here's what I would say. IS times NS is equal to IP times NP. To me, that makes more sense to keep them like that. Okay? And then IS would be IP, 10.0 amps, times NP, which would be 550 turns, and divide that by NS. Okay? And that would be, is that 2,500? I can't read my ugly writing. Turns. Okay? I would do it that way rather than the ratios, because to me that's too similar to the other, but it's got them reversed. I would go with the product rule rather than a quotient or a ratio. What you get IS to be? 2.20 amps. Okay? Now, that is a step-up transformer, but it's dropping the current, because whatever the voltage is doing, which would be stepped up, the current has to be in reverse and brought down. Okay? And then they do the one I just said, and I think this is the better one to use for current. Okay? And then always remember this, P is equal to IV, which is power is equal to current times voltage. So let's do example 6 quickly. The power in the primary coil of a transformer is 375 watts. So PP is 375 watts. Okay? If the current in the secondary coil, so that would be I sub S, is, 14.4 amps, what is the voltage in the secondary? Well, guess what? PP is going to be the same as PS, because you assume no power loss. So, to get the voltage, PS is equal to IS times VS, and to get VS, it's PS divided by IS, and that would be 375 watts divided by 14.4 amps. 11.4?
No.
Oh. I miswrote it. Sorry about that. Okay. It's 11.4. Okay. Yeah. 375 divided by 11.4 is 32.9 volts. Okay. Now, They didn't tell you anything about what the primary side of anything was, but the voltage. But I'm guessing this was probably a step down transformer because that's a pretty low voltage and a fairly high current. But they didn't say it. All right, now comes this figure. This is showing a hydroelectric dam. I don't know if you can follow that. But they're creating electricity there. The running water is turning a turbine. The turbine has in it those magnets, and the changing magnetic field induces a current. There they have huge step-up transformers that raise that voltage to 6,600 volts. Really high voltage. Okay? They take that and send it to, I guess they're saying that stepped up even higher, and then the high voltage power lines are stepped up to as much as 132,000 volts. That's really super high voltage, okay? Then it comes into the city, and those are the big lines that you see taking it cross country, basically. Really, really high voltage, very, very small current. Going long distances minimizes the line loss. Then you come into town and you have substations, like I was talking about at UAB, that steps it down significantly, back down to around 6,000 volts. And then before it goes into your house, there's another transformer stepping down to get to 110 or 220 volts. Actually, some of it will get it down to 330 or so, and then they split off the 110 from the 220. Does anyone know what uses 220 in your house? Basically the things that produce a lot of heat. Your oven, or your range top, your clothes dryer, your air conditioning usually. If you have things like that, those are your high voltage because they produce a lot of heat, and they want those at higher voltage. Okay. And that led to 19.2. Now, we did not get to inductance. Sorry about that. I'm not sure if y'all will ever even need that. I don't know. I don't know how much detail you get into in this. But basically, inductance, think of it like those solenoids, okay? An inductor is in some ways like a resistance, but not quite the same thing, because it's using current to produce if we can't go over it, I can't think of a simple way to say it. You can look at this in the book and see what you got. You'll see there, though, that very first formula, 1 Henry, that's inductance, is 1 ohm second. So it's like a resistance, but it's a delayed resistance, I guess, is one way to express it. So anyway, if you need it, you know where to find it in the book, okay? Hopefully you won't need it. Sorry if we didn't get far enough along for you. Okay. All right, that does it for, I can't believe that's it for chapter 19, period. They have no other slides in the thing, so I guess it's a good place to start. What's that? Okay, that's what I was going to ask you. I can easily come over. Well, wait, Wednesday, I may be on this campus anyway, on the West Campus. There won't be any problem at all for me to come over here at 4 o'clock. You want me to do that? What's that?
Can we email you?
You can email them to me. Now, let me ask you to do this.
Okay.
A lot of people, when they're doing things like this, will take a picture with the phone and send me the picture. Yeah, I'd rather have PDF, because my old computer, this one will read it, but the old computer that's hooked to my printer, it will not do JPEGs or any of the other picture files. It will read a PDF. So if you can scan it and get it to PDF and send it to me that way, that's far better. If you can't, go on and send me the JPEG. I'll just take it to somebody else and get them to download it for me. Say that again. Can you try to have them in by the end of business on Wednesday, like 6 o'clock Wednesday? Yeah. Earlier is better, but you see, here's the deal. I'm going, if possibly Thursday morning, but make it pretty early Thursday morning. I think we're leaving for Tallahassee at 10 o'clock. And so I'm not going to I'll be over here on the Birmingham campus again. I really don't have a printer, but I can probably use the secretary's printer or something like that to print things off. But I need to have them in fairly early because we'll probably be loading the bus or van, maybe as early as 9:30 or something like that. So if you don't get them to me by 6 o'clock Wednesday, now do you want me to be over here Wednesday? Would that be convenient for anybody?
What time do you leave Wednesday?
What's that?
What time are you going to leave campus on Wednesday?
Like I said, I'll be over there already. I can come over here at 4 o'clock just like regular class.
What time will you leave?
Leave 6 o'clock.
Oh, okay.
Yeah, just like
So you're
normal.
not going to be at Bessemer on Wednesday?
Say again?
You're not going to Bessemer on Wednesday?
I'll probably be there in the morning because I have a student coming to do a makeup test. See, what I have on Wednesday, I have a meeting at 11 or something like that over here. So I've got to, if I go to Bessemer, then I've got to come over here, and then I'm trying not to drive back to Bessemer because I'll just stay and work the rest of the day here. So is Bessemer more convenient for you?
I was just trying to.
What's that? What is more convenient for you? Is Bessemer more convenient? Or not?
I mean, I'll be at Bessemer in the afternoon.
Oh, you
I'm
will?
gonna be here. I thought you were going to be at Bessemer on Wednesday.
I was until that meeting was
So
called.
The meeting called, so you got to come back over here at 11
Yeah.
Wednesday. And you stay over here till 6.
No, I can go back there. If no one's coming here from 4 to 6, I can go back to Bessemer. But see, if I've got to meet a student in the morning at Bessemer, and then I got to be over here at 11, and then if I need to go back to Bessemer and then come back here, I'd rather not do that much traveling. But I can be any place, anytime. Just let me know what's more convenient for you. If you want me here 4 to 6, that's on my schedule. And then probably what I'll do is stay here after the meeting and not go back there. But if that's more convenient there, then I can go back there and not come back here at 4.
What time are you going to be here Wednesday? Wednesday, 11 o'clock.
11 o'clock, I'll be over there on the West Campus.
Where? Where actually?
Okay, yeah. Now, if you want to do that, if Bessemer's more convenient for you, take it by there anytime, slide it under my door. You know where my office is on Bessemer campus? Okay, it's in the A building. In the A building in room 265. 265.
Okay. That's your office?
That's my office. And you'll see my locator card on there. So yeah, that's a possibility.
So you have to drive back over there. You stay here, and then
We'll just slide under the door.
Okay. And I won't pick it up until Monday morning then, so you won't see your grades until sometime Monday or later. Okay.
What time are you going to leave on Wednesday?
Second?
What time are you going to leave on Wednesday?
okay, that's all you gotta do.
Okay.
Take people.
I'll go to Bessemer campus in the morning. I'll get there about 7:45. I'll leave there about 10:30 and come over here for my 11 o'clock meeting. I'll stay here until around 6. If you want me to come to this campus, I'll be here from 4 to 6. Does anyone want to bring the things here from 4 to 6? Let me find that out. Does anyone want me to come here from 4 to 6? It's no problem for me to do so. Nobody needs to be here. So I'll be, okay, do you know where Dr. Pruitt's office is over there?
Yeah, we're fine.
Okay.
I'll be in your office under your door.
Okay. The one in Bessemer.
What about you?
We'll see you Monday morning.
Okay. Okay.
No.
So we won't.
My paper will see you. I'll see your paper. Okay.
Yeah.
So we
See you
highlight from Monday to Friday, right? If he has to get it.
No, he said it has to be turned in by Wednesday by 6 o'clock.
That's technically when they're due, but look,
She's saying, can you bring it Monday and slide it under your door?
absolutely.
No, that's what he's saying. You have till Monday to slide it
Yeah.
under the door.
The thing is, from Wednesday evening until Monday morning, I won't know when you slid it under there. So anytime, if you can get it to me sooner, that's fine. But if you can't, then anytime before Monday morning. Okay, good deal. Enjoyed having you as class. Did y'all do student course evaluation? I meant to ask that before people left.
No, we're gonna do it.
Yeah, fantastic. Thank you. All right, take care.